All right, today we're going to pick up where we left off and look at Newton's second and third laws. So we talked a little bit about forces and what a force is. It's a push or a pull. And we started with the first law that things are going to keep doing whatever they're doing until we put a force on them and cause them to change. So now we're going to look a little bit different at how that change occurs. So Newton's second law says that the acceleration that we get for an object is directly proportional, that means as one goes up, the other goes up, to the net force acting on it, and inversely proportional to its mass. If we put that into the form of an equation, here's your very first math equation that we have in this section. It's F equals ma. So the force that's applied will take the mass of the object and give it an acceleration. Okay? The more force, the more acceleration. The more mass, the less acceleration. If you have something big like an elephant that you're trying to push, you have to use a lot more force to get it to change its motion than if you had something small like a baseball. So directly proportional force and acceleration, more force, more acceleration. And then acceleration is inversely proportional with mass. The more mass you have, the less it's going to accelerate given a certain force. Now, one of the forces that we're in constant contact with is our gravitational force, and that's the force that pulls us towards the surface. And all objects have gravity, but because we're on the Earth and the Earth is so big compared to the things around us, then that is usually the most gravity that we feel. But honestly, all objects have some gravitational force. It's just pretty much canceled out by the force of the Earth pulling down on us. Now, the magnitude of that force that we feel is called weight. So there's your big difference between mass and weight. Mass is the amount of stuff that we have in us. Weight is how gravity affects that stuff. So on Earth, we're pretty used to using weight and mass interchangeably. But if you were to take your mass, how much stuff you have on you, in you, and go to the moon or go to Mars or hang out in a space station, your weight would be very, very different because gravity is going to affect you differently. Now here on Earth, gravity and the acceleration due to gravity is 9.8 meters per second squared. We use that when we use projectile motion, right? Now we're going to pull that in and use it with forces. So the weight force, so you remember F equals ma, the weight force, W, is equal to the mass times the acceleration of gravity, which we'll use g. So it looks like I've given you another formula here, W equals mg, but it's really F equals ma, just more specific to talking about weight. So let's practice here. If a woman has a mass of 50 kilograms, what is her weight in newtons? I want you to try this and then check yourself. All right, so did you get kind of a big number? It's very typical for students to see big numbers and think, oh my gosh, this woman's huge, but she's really not. If you were to take that and convert it over to pounds, it's only about, I think it was 110 pounds. So this is really not a gigantic woman. It's just we're so used to seeing pounds that when you see it in the form of newtons, it seems gigantic. It's really not. Susie Small finds that she weighs 300 newtons. Now I said small. Susie is small. She weighs 300 newtons. It sounds like a big number, but that's because we're used to thinking pounds. What is her mass in kilograms? Try this one. All right, did you get it? Awesome. So let's jump from the second law into the third. Now we've got an interaction between objects, whether we're pushing on that elephant or throwing a baseball or sitting in a chair like this lady here. If we've got two objects interacting, Newton's third law says that the forces between those objects are exerted in equal magnitude but opposite direction. So the lady sitting on the chair is balanced by the chair holding the lady up. If we get an unbalanced force, if they're not the same, that's when we get an acceleration with Newton's second law. For instance, if the chair were to suddenly break, it could no longer be equal and opposite to her weight force. Then she would accelerate by falling down to the ground. So our forces always come in pairs. They're always interacting and pushing on each other, resisting each other. And then whether or not it's balanced determines whether or not we get acceleration with the second law. So look at the jet plane. This is a jet engine. You can see air comes into the front of the jet plane. It compresses and shoots backwards. Now, the gas from the jet goes backwards, and rocket ships work the same way. The gas goes one direction, but because the force is in a pair, it pushes the jet plane forward. So gases are going backwards, plane is going forwards because of Newton's third law. And if you've ever had like a paintball gun or you're target practicing or whatever, you might have noticed some kickback or some recoil. That's Newton's third law. When you shoot a gun, the bullet, because it's a very small mass, goes very quickly one direction, while the bigger mass, the rifle, the paintball gun, whatever, goes back the other direction. But you don't notice as big of an acceleration backwards because there's more mass. Remember in second law, F is ma, same force, opposite directions, but the smaller mass will get the bigger acceleration, that's the bullet or the paintball, and then the bigger mass will get the smaller acceleration. So when we look at all these different pairs of forces, whether it's weight and normal force, or whether it's force going this way and force going that way, whenever you look at all of the combination of forces, what we get when we have a leftover force is called the net force. And it's important to remember force is a vector. It has a magnitude, it has a direction. So when we look at all of our forces, we can combine them the same way we did displacement. If they're going in the same direction, so if we've got two people pushing on a desk trying to move it across the floor, then their forces will add together. If they're pushing against each other, then their forces will be subtracted. And if they're at angles, then we use our good old-fashioned trigonometry to figure that out. So let's practice real quick. If we've got two forces horizontally applied, 225 newtons and 165 newtons, they're going the same direction. We're pushing a crate across a warehouse floor. What's the horizontal force on that crate? Okay, now try it where the forces are exerted in opposite directions. Now we've got somebody tricking us and trying to stop us from doing our work, right? If they're in opposite directions, what's the net horizontal force on the crate? All right, now it's a little tricky. We've got a force exerted towards the north, and we've got a force exerted towards the east, whichever direction that is. So find the magnitude and direction of the net force. Now we've got them at an angle. So with our little triangle, what you gonna do? All right, so let's look at a concept called equilibrium. Equilibrium has that word equal in there. When your forces are equal and opposite, when they're balanced out, when they're the same as each other but balancing different directions, then we get a balanced equilibrium state. So if you're kind of a mathy brain, what's happening is all of our force vectors add up to zero. Everything cancels out. So can things be moving and still at equilibrium? Well, we're thinking F equals ma. You can't have acceleration if you don't have a net force, right? But keyword in there is acceleration. Acceleration is a change in our movement. Equilibrium is a state of no change, but it doesn't mean it's not moving. It's just not moving faster and faster or slower or whatever. So if an object is going in a straight line with no change in its speed, then it can be at equilibrium. So think about the race car down here. We've got the force from the road pushing the car forward, the tires against the road. We've got air resistance that's balancing that out. We've got the weight, the normal force. If those are all balanced, we could be moving at a constant velocity. We could be on cruise control. Or think like terminal velocity when we're parachuting. The purpose of a parachute is to increase the air resistance so that it balances our weight. That's why there's different sizes of parachutes for different sizes of people, or even cargo if you're throwing cargo out of a plane. You want that air resistance to be balanced by the weight. Now, that doesn't mean that once we open our parachuters just stop and hang there in midair. That would be kind of awkward to see around town, right? No, they keep moving. They just stop accelerating. They've reached a velocity at which that's as high as they're going to go. They're not going to get faster and faster. Now, we talked already a little bit about normal force. That's our support force. That normal, remember, again, doesn't mean not strange. It just means at a right angle to. So our table can supply a force to support whatever's sitting on top of it, in this case a laptop, or the scale is measuring the normal force applied to the guy to be equal and opposite to his weight. And so that just means that it's at a right angle to our surface. Now, Remember, as our surface moves, so does our normal force. Now, another force that we want to talk about is friction. Friction causes a resistance to motion. Now, it could be equal and opposite to our object. In that case, it's not going to move. But if it's not able to be completely equal, then it's just going to try to slow it down. So it's a resistance force. It arises from contact between two forces. The force of friction has to be smaller than or equal to the force that's applied. You're never going to have a bigger force of friction. That's never going to happen. It's only resisting. And when the force applied gets big enough to overcome friction, that's when it'll slip and move. To calculate friction, we've got this funky little Greek letter in there. It's called a mu. And to calculate friction, we have the force of friction is equal to the mu times the normal force. Now, the mu is a coefficient of friction. It doesn't have any kind of value at the end, like kilograms, meters. There's no label to it. It's just literally a number. It's going to be between 0 and 1. So if you're getting numbers bigger than 1, you must be dividing somewhere in there incorrectly. And it's going to be unique to that surface. So different surfaces will have different mu's. Ice will have a very low mu. Concrete will have a very high mu. And it's a property of that substance or that surface between the two of how much it's going to resist that motion. So we have two types of friction. We've got static friction. Static, think it's clinging, it's trying to keep it from moving. Kinetic friction is moving friction. So static is going to be higher. It's harder to get things to move because of inertia. They want to keep doing what they're doing than it is to stop them from moving. So kinetic friction is always going to be a lower number than your static friction, but they're calculated the same way. F of F equals mu F of N. And you might see me refer to this as our fun formula because of F, mu, N, fun. I know you probably aren't going to think it's fun, but I think it's fun to call it that. So try this. We've got a boy exerting a 36 Newton horizontal force. So he's pulling with 36 Newtons as the applied. He's pulling a 52 Newton sled across a cement sidewalk. Now the 52 Newton sled means that that's how much it weighs, meaning that must be the supporting normal force because it's not falling through the ground and it's not flying out into the sky. So the 52 Newtons down must be balanced by 52 Newtons up. So in our fun formula, F of N, there's your 52 Newtons. It's at a constant speed, which means that we're not accelerating. So our force applied must be balanced by the force of friction. You see where we're going here? So F of F, force of friction, must be that 36 because it's equal and opposite to his applied force. So now that you've got your numbers, what's the coefficient of kinetic friction between the sidewalk and the metal runners? Okay, try the fun formula and see if you can get it. Okay, now we're going to change things up a little bit. Now we've got the same sled, 52 Newtons for our normal force and our weight force, but we're going on packed snow instead. The coefficient of friction is now only 0.12. If we've got a person that weighs 650 Newtons sitting on the sled, in addition to the 52 Newton weight of the sled, now how much force are we going to need to pull the sled across the snow at constant speed? So you're solving for that force of friction that's going to balance out your applied force. All right, did you get it? Fantastic. So this is the end of our Newton's second and third law. You've made it through, and we've only got 3 formulas, I believe. F equals ma, W equals mg, and our fun formula, F of F equals mu F of N. So this is a way easier math-wise section here. I'm hoping it's a good break for you after projectile motion. So make sure you've got all your notes. We'll start practicing with this in labs and practice problems, and we'll see how you do.